In this lesson, we'll look at how episodic memories can contribute to the formation of semantic memories. In a previous lesson, we saw a diagram like this. On the left, we might know information about a person, and that would be in our semantic memory, but we might also be able to retrieve specific memories of interacting with that person. In other words, we would have episodic memories. But there's a lot of information about the world that we know, and we have lost access to the specific episodic memories. So semantic information, semantic memory, is filled with information that originated from an episodic memory, but we've lost access to that episodic memory. So there's a transformation. Much of what we learn in our lives, of course, is happening in episodes. But as we fill up our semantic memory with information, that information has lost the where and the when of the learning episode. So we'll take a look at an example of what might be going on as an episodic memory is transformed into a semantic memory, with the resulting loss of the sort of timestamp of the learning episode. Now, to begin, let's consider what we know about semantic memory, or how we think it might work. First of all, semantic memory stores information in non-random ways. And to see this, consider what you know about birds. If somebody were to ask you, what's a bird, you might say, well, it's an animal. It has feathers and it can fly, and you might be able to give some examples, a robin and a canary, and with the canary you might be able to tell us some attributes of the canary. In other words, the idea is that semantic memory is organized according to associations and categorical relationships. When we learn something new, we don't just sort of randomly store it in our memory system, we link it to things that it's associated with. So for example, if you learn something new about canaries, you would be linking that new piece of information to this already existing network. You wouldn't be storing that new piece of information in some place that it had no links to the other information you knew about canaries. So that's the idea with semantic memory, is that it's an association network. And when we learn something new, we are integrating that new information into already existing knowledge. And in a previous lesson, we also learned something about trace transformation theory. And the idea there was that system consolidation transforms a memory from detail-rich and context-specific memory into a more generalized version of the memory that can be integrated with other stored information in semantic memory. The memory becomes more schematic, but hippocampus independent. The hippocampal memory trace remains necessary for retrieving vivid and detailed episodic memories. So this is what we'll do. We'll try to give a concrete example of how a couple of episodes can be transformed into a semantic memory. And the idea is there's going to be an extraction of the general features between those episodes that will result in the formation of a semantic memory for whatever the common features were from those episodes. The example we use is going to the zoo and seeing some tigers at the zoo, or see a tiger. Now we know from previous lessons that all the perceptual information of what's happening to us at the moment is fed down into the hippocampus, so that's a convergence site, and then the hippocampus is going to be involved in the consolidation of that memory. So if we think about what's going on in the hippocampus, we've seen in past lessons that the memory for Tiger 1 at Zoo 1 will involve changes in synapse strength in the hippocampus. So here we have our sort of little icon for synaptic plasticity among hippocampal cells. We have a memory trace for Tiger 1 at Zoo 1. But there also, of course, there was cortical activity, right? So the cortical systems were processing Tiger 1, and there is this link early on, right? The hippocampus may be a pointer for the reactivation of the cortical part of the memory trace, but early on the cortical memory trace is weak, and so we need the hippocampus to retrieve the memory. Now I've also indicated here another sort of a representation in the posterior part of the hippocampus. So scientists now are starting to become interested in this axis of the hippocampus, the anterior hippocampus and the posterior hippocampus. They seem to have different functional connections, and that may be significant in how an episodic memory gets transformed into a semantic memory. So for our purposes, we're going to say that the memory trace for Tiger 1 at Zoo 1 has an anterior component and a posterior component. So there were changes to synapses in hippocampal cells that make the memory trace for Tiger 1 at Zoo 1, and these hippocampal memory traces are linked to the cortical, the weak cortical trace initially. Now in this picture we see the hippocampus situated underneath the temporal lobe, and researchers now looking at the functional connectivity with the hippocampus suggest that the posterior part of the hippocampus has more intimate ties with posterior perceptual regions. The anterior part of the hippocampus has more intimate connections to some of the anterior parts of the brain, temporal pole and the ventromedial prefrontal cortex, the amygdala. And there are some differences in the structure of the hippocampus along this axis. There's a larger CA1 field in the anterior hippocampus, and there's a higher dentate gyrus to CA3 ratio in the posterior hippocampus, smaller receptive fields in the posterior hippocampus. So it is possible then that the anterior and the posterior parts of the hippocampus are functionally doing different things, or they're making different contributions to memory. Now let's return to our Tiger at the Zoo episodes. Let's say we go to another zoo, Zoo 2, and we see Tiger 2 at Zoo 2. Now remember, the hippocampus is good at pattern separation, so we're going to have a non-overlapping hippocampal memory trace for Tiger 2 at Zoo 2. It'll have an anterior component and a posterior component. But up in the cortex, while there may be some unique cortical cells that are active for Tiger 2, there is presumably some overlap, some overlapping activation, because Tiger 2 is similar to Tiger 1. And it's this overlapping activation that scientists hypothesize might be the basis for representing the concept of tiger. Now, at this time, if someone were to ask the person to remember the tiger at Tiger 1 at Zoo 1, they might be able to retrieve a detailed and detailed, rich, and context-specific memory of Tiger 1 at Tiger 1 at Zoo 1, and that would be the kind of the pink memory traces here in the hippocampus and the cortical trace here. And then if we ask, oh, remember Tiger 2 at Zoo 2, can you call up an episodic memory of that? Well, then that would activate the green traces here in the hippocampus and the cortical trace. So as long as the person can reactivate these hippocampal traces here, the person would have access to the episodic memories, the detail-rich, context-specific memories for Tiger 1 at Zoo 1 and Tiger 2 at Zoo 2. But over time, as consolidation happens, some researchers suggest that there's going to be a preferential sort of consolidation of the common features of Tiger 1 and Tiger 2 that will result in sort of the semantic memory, the schematized version of a tiger at a zoo. And so if we ask the person at a later time, think about a tiger at a zoo, the idea is that it's the common pattern of activation, Tiger 1 and Tiger 2, that's what gets reactivated during retrieval. And this would be kind of a semanticized memory of a tiger at the zoo. So and we can think of this as sort of like the concept of a tiger. It has lost its specific episodic details. It's rather just information about a tiger at a zoo. And the way we could kind of represent that now with this anterior-posterior distinction is that maybe when we're retrieving the kind of schematized or semanticized memory for a tiger at the zoo, we're not activating the posterior hippocampal trace. So with no reactivation in the posterior hippocampus, we get a loss of the perceptual detail, the vividness, and the context specificity. So here we see on this trace transformation theory, some researchers are now hypothesizing that maybe this distinction between anterior and posterior hippocampus is involved in this transformation of episodic memories being transformed into more semantic types of memories, where we can call up a memory of a tiger at a zoo, but it's a kind of a general memory. It has lost the specific details. It may be because we're not activating that posterior part of the memory trace. But of course, you'll remember in the case of HM, HM had lost his hippocampus entirely bilaterally, yet he still seemed to have some semanticized memories of his past. And so it's possible that even the anterior part of the hippocampus is not needed. So it may not be needed for remembering the gist of the tiger experience. It may well be that the cortical representation of the tiger could be activated by other brain systems besides the hippocampus. So in summary, the idea is that while we can have specific episodic events, tiger 1 at zoo 1, tiger 2 at zoo 2, and we can have non-overlapping episodic memories for those events, if there are common features of those events, the cortical representation can show this overlapping pattern then. And it's the overlapping part of the memory representations that then, in a sense, may later on be retrieved as semantic memories of tigers at the zoo.